At the bottom of our oceans lies a realm where sunlight cannot reach, where pressure crushes steel and temperatures plunge into freezing cold. For centuries, the deep remained hidden from human eyes. Now, thanks to technological advances, we are beginning to understand this alien world. The planet's final frontier extends thousands of meters beneath the surface, a domain where life adapts to extremes beyond imagination. What waits at the absolute limit of our world remains one of humanity's greatest mysteries. Pressure at the deepest points of the ocean exceeds 1,000 times the surface level. At the Challenger Deep, the water column creates forces that would flatten a building. The hulls of submersibles must withstand immense weight to descend safely. This relentless force shapes everything from geology to biology, creating environments where only the hardiest life forms can exist. Even the smallest organisms feel the squeeze, their bodies compressed to remarkable degrees. In the absence of sunlight, life has evolved extraordinary adaptations. Bioluminescent creatures produce their own glow to attract prey, mates, or predators. From glowing worms to eerie jellyfish, the deep sea pulses with otherworldly light. These organisms thrive in darkness, using luminescence as both weapon and signal in an environment where sight is the only guide. The glow comes from chemical reactions inside specialized cells, producing light without heat. On the seafloor, hydrothermal vents spew superheated mineral-rich water from the Earth's crust. These vents support entire communities independent of sunlight, relying on chemosynthesis rather than photosynthesis. Tube worms, shrimp, and bacteria cluster around the vents, forming oases of life in the pitch-black ocean. Scientists study these systems to understand the origins of life itself. The chemical energy from the vents fuels entire food webs, demonstrating that life can flourish far from the sun. Human exploration of the abyss began with simple bathyscaphes that carried a few scientists to the edge of the deep. These early vessels proved the limits of engineering and endurance. Today, larger submersibles carry multiple researchers, equipped with cameras and sample collection tools. The descent takes hours, and the journey requires meticulous planning. Despite decades of effort, barely a fraction of the deep ocean has been explored. To map the abyss, sonar technology sends sound pulses downward and measures their return time. The speed of sound in water varies with temperature, salinity, and pressure, allowing scientists to calculate depth and terrain. Detailed maps reveal mountain ranges, valleys, and even small seamounts on the seafloor. Sonar also detects marine life by picking up echoes from swimming animals. This invisible mapping technique has transformed our understanding of the deep ocean's three-dimensional structure. Modern remotely operated vehicles carry bright lights and robotic arms to explore dangerous zones. These unmanned machines can withstand pressures that would destroy a regular camera. When they encounter unusual creatures, they transmit live video back to the surface. The ROVs navigate complex terrain with precision, collecting samples and imaging habitats. Their presence allows scientists to observe behavior without disturbing the delicate ecosystems. Crewed submersibles offer the closest experience to the deep, allowing humans to see directly. The first successful crewed descent was a milestone in exploration. Modern vessels provide comfortable cabins, control panels, and life support systems. Crew members conduct experiments, collect biological specimens, and document geological features. The psychological challenge of isolation in such an environment tests human resilience. Despite scientific progress, human activities threaten the deep ocean. Plastic waste drifts on the seafloor, accumulating in deep trenches. Mining operations seek rare minerals along the continental margins. Both pollutants introduce foreign materials into fragile ecosystems. The noise from shipping and seismic surveys disrupts communication among marine life. Protecting the deep requires international cooperation and sustainable practices to preserve this unique habitat for future generations. The deep ocean plays a critical role in global climate regulation. It stores vast amounts of carbon dioxide and absorbs excess heat from the atmosphere. The circulation of deep waters helps distribute warmth around the planet. Disruptions to these systems could accelerate climate change. Additionally, the deep contains unique chemical compounds that influence ocean chemistry. Understanding these processes is vital for predicting environmental changes. The Challenger Deep holds the record for the deepest point on Earth, reaching nearly 11 kilometers below sea level. Its name honors the pioneering explorer who first attempted to cross it. Researchers have measured its depth precisely using sonar and submersible technology. The extreme conditions there create a natural laboratory for studying extremophiles. Future missions may deploy advanced sensors to monitor environmental changes. The future of deep ocean exploration lies in smaller, more agile vehicles and artificial intelligence. New submersibles can travel faster and explore narrow crevices. Autonomous drones can survey areas too dangerous for humans. These innovations promise to uncover even more secrets of the deep. Yet fundamental questions remain: how does life adapt to such extreme conditions? What lies beyond the next unexplored trench? The journey continues, driven by curiosity and the desire to understand our planet's final frontier. The Mariana Trench in the western Pacific Ocean contains the deepest known point on Earth's surface, a depression called Challenger Deep, which plunges nearly 11,000 meters below the ocean's surface. To put that in perspective, if Mount Everest were placed at the bottom of Challenger Deep, its summit would still be more than 2 kilometers underwater. This is a place where sunlight never reaches, where temperatures hover near freezing, and where the weight of the water above creates pressure more than 1,000 times greater than at the surface. For most of human history, we knew almost nothing about what existed down there. At the bottom of the Mariana Trench, the pressure exceeds 1,000 atmospheres. That is roughly equivalent to balancing 50 loaded jumbo jets on a single square inch of surface. Most ordinary materials, wood, glass, even standard steel, would be crushed instantly. Only specially engineered submersibles, built with thick titanium spheres and designed to distribute force evenly, can withstand such conditions. This extreme pressure is the single greatest obstacle to deep ocean exploration. It is the reason that more people have walked on the moon than have traveled to the deepest point of the ocean. In January 1960, two men, Swiss oceanographer Jacques Piccard and U.S. Navy Lieutenant Don Walsh, descended to the bottom of Challenger Deep aboard the Bathyscaphe Trieste. The descent took nearly 5 hours. At around 9,000 meters, they heard a loud crack. A window had fractured under the pressure. But the layered glass held, and they continued down. When they finally reached the seafloor, they observed something unexpected: a flatfish swimming slowly away from the light of their vessel. It was the first proof that complex life could exist at the very bottom of the ocean. Below about 1,000 meters, the ocean enters what scientists call the midnight zone, a region of total and permanent darkness. No sunlight penetrates this deep. Plants cannot grow here because there is no light for photosynthesis. Every organism that lives in this zone must survive by feeding on whatever drifts down from above, a slow rain of organic particles known as marine snow, or by hunting other creatures in the dark. The ecosystem is sparse, slow-moving, and extraordinarily efficient. Nothing is wasted in the midnight zone. In a world without sunlight, many deep-sea organisms produce their own. This phenomenon is called bioluminescence, and it is one of the most common forms of communication in the deep ocean. Jellyfish, squid, fish, and even microscopic plankton generate light through chemical reactions within their bodies. Some use it to attract mates. Others use it to lure prey. Still others use it as a defense, a flash of light to startle a predator or to camouflage themselves against the faint glow from above. In the deep ocean, light is a language, a weapon, and a disguise all at once. The animals of the deep ocean look unlike anything on the surface. The anglerfish carries its own fishing rod, a bioluminescent lure dangling above its enormous, tooth-filled mouth. The gulper eel can unhinge its jaw to swallow prey nearly as large as itself. The giant squid, once thought to be a myth, can grow to over 12 meters in length and has eyes the size of dinner plates, the largest eyes of any animal on Earth. These adaptations are not accidents. Each one evolved in response to a world where food is scarce, space is vast, and every encounter could mean survival or death. In 1977, scientists exploring near the Galapagos Islands discovered something that reshaped our understanding of life on Earth. At the bottom of the ocean, around cracks in the Earth's crust, superheated water bursts upward from below the seafloor. These are hydrothermal vents, and despite the total darkness and toxic minerals, they support dense communities of life. Giant tube worms, clams, and shrimp thrive here, powered not by sunlight but by chemosynthesis, bacteria that convert chemicals from the vent water into energy. It was the first ecosystem ever discovered that does not depend on the sun. The deep ocean is not a flat plain. It is a landscape as dramatic as any on land, with towering mountains, deep canyons, and vast plateaus. Seamounts, underwater mountains formed by volcanic activity, rise thousands of meters from the seafloor. Some of the largest, like the Hawaiian Emperor Seamount chain, stretch for thousands of kilometers. These underwater mountains create currents that bring nutrients up from the deep, supporting rich ecosystems in the waters above. There are estimated to be tens of thousands of seamounts across the world's oceans, and the majority have never been surveyed. Sound travels more than 4 times faster in water than in air, and in the deep ocean, it carries for enormous distances. Whales use this to communicate across entire ocean basins, producing low-frequency calls that can travel hundreds of kilometers. But the deep ocean is also a place of profound quiet. Away from shipping lanes and human activity, it is one of the few environments on Earth still largely untouched by noise. That is changing. As human activity in the ocean expands, shipping, drilling, sonar, the acoustic environment of the deep is being altered in ways we are only beginning to understand. Despite decades of effort, the vast majority of the deep ocean floor remains unmapped. Current estimates suggest that less than 25% of the global seafloor has been surveyed to modern resolution standards. Most of what we know comes from satellite measurements, which can detect large-scale features but miss the fine detail. Only direct surveys, using sonar from research vessels, can produce high-resolution maps of the seafloor. At the current rate of mapping, it would take decades to complete a full picture of the ocean floor. It is the largest unmapped region on Earth. Every major expedition to the deep ocean discovers species previously unknown to science. Some estimates suggest that the deep sea may contain hundreds of thousands, perhaps millions, of species that have never been described. New species of fish, crustaceans, worms, and microbes are identified regularly, even as their habitats face growing threats from deep-sea mining, pollution, and climate change. The deep ocean is not empty. It is full of life we have never seen, living in conditions we can barely imagine, in a world that has existed for hundreds of millions of years before the first human ever looked beneath the waves. The deep ocean is the largest habitat on Earth, and it is also the least explored. It covers more than half the planet's surface, yet we have studied only a fraction of it. Every descent reveals something new, a species, a geological feature, a chemical process that changes our understanding of how life works. The deep ocean is not merely a place of darkness and pressure. It is a living archive of Earth's history, a reservoir of biodiversity, and a frontier that remains wide open. If you enjoyed this story, subscribe for more real mysteries and discoveries.